And we're actually not going in order from chapter 7. I think it makes more sense to do it this way and save all of the math part for next week. So we're starting now at 7.3. We're going to do this part about chemical equations and reactions, and then we'll go into the mole relationships next week.
That's very, very not fun.
Well, I guess that depends on your perspective. How would you rate all the stuff we've been doing so far?
Not very fun.
All right, so it's probably more of the same then.
Part of the course then, right?
Yeah, probably pretty much, yeah. Yeah, I think that's fair. Sorry. I'll let you know if we're going to do something that's really fun.
Okay.
We are going to blow up pumpkins pretty soon, so that'll be fun. Yeah. Because you can only get them this time of year. Like, they only come out now. So we'll blow up some pumpkins. No. We'll just do it in a controlled way in here. Yeah, or in here maybe. I don't know. We'll see. Depends how much you want to clean up. Okay. All right. So you've probably seen some of these things before. I know you've seen some of these things before in lab, but we didn't really talk about what they are, what they mean specifically. So today we're going to look at all of the precise ways that we need to write chemical equations and what they are. So chemical equations are things like this. And we're going to do a bunch of chemical equations in lab next week too. So it's telling you what happens in a chemical reaction. Now the equation is not the reaction itself, it's just a way of describing the reaction. So in this case, we're saying that hydrogen gas and oxygen gas are combining to make water vapor. So a few things we can get from this, what we've written so far. First, we got the formulas, of course, so that tells you what is being reacted or what is forming. We can talk about the two sides of the chemical reactions, So we can say that on this side, we have the reactants, sometimes called the reagents, the reactants, the things that are reacting. And on the other side, we have the products, in this case, just one product. Reactants and products are given by the arrow, the fact that the arrow goes from left to right. Not all chemical equations have an arrow going from left to right. We're going to see some where the arrow can go both ways. Sometimes we can talk about the backwards reaction going right to left. So whether we have reactants or products is not dictated by the position on the paper, but by the arrow. So where are you starting and where are you going based on the direction of the arrow. Most of the time, this is the common way to write it. You start with the stuff on the left and you go to the right, but we'll see some examples where that's not the case. So that's something that we can see from the chemical equation. What we start with, what we end with. Another thing we can see is the states of the reagents, which is what's given in that little parentheses here. So we've got G for gas, L for liquid, S for solid. And then we use this other one sometimes, AQ, which stands for aqueous, which means dissolved in water. So when we had all those solutions in lab on Tuesday, they were aqueous solutions. If we were to write out those chemical reactions, we would have said things like calcium chloride, CaCl, parentheses, AQ, because it was calcium chloride dissolved in water. So that's what an aqueous solution is. So those are the four things we'll use there. You'll see these in chemical reactions. When you're asked to write a reaction, like a reaction you don't know, like one of the things we'll do by the end of this, say things like, what happens when this chemical reacts with this chemical, write the equation. And you'll try to write out the equation. You may not know what the states are going to be at the end because, you may not know. So that's okay. We don't always know what the states are if we haven't actually physically done the reaction. But if it's given in the problem, we can list them there. All right. And then the other thing we can know is the ratio that the reactants react in and the products are formed in relative to the reactants. So there's actually a problem with this as it's written right now. Does anybody see what it is? It violates the a really core principle of stuff. Yeah, exactly. If we count up the atoms involved in this reaction, we have a problem. So let's draw them out in their actual shapes, like molecules. So what we see on this side is a hydrogen molecule, HH, and an oxygen molecule, which we know has a double bond in it. So those are the two things that we're showing there. And we're saying that the product then is a water molecule. Like that. So if we look at what's happening there, we could count up the different atoms that are used, and we might notice a problem. So on this side, I've got 2 hydrogen atoms and 2 oxygen atoms. On this side, I've got 2 hydrogen atoms and 1 oxygen atom. So according to my chemical reaction, an oxygen atom has just disappeared. And that's not okay. Because matter doesn't just disappear. Matter is always conserved in chemical reactions. So we can't magically appear atoms, we can't magically disappear atoms. So what does that tell us about our reaction? It tells us something's not right here, and we have to correct it. So let's first talk about ways not to correct it. We can't correct it by simply adding an O as one of the products. Why isn't that okay? It's just, yeah, so one thing is we know oxygen atoms don't just hang around by themselves. And we can't just add stuff to equations, because you could actually do this reaction, and there are no oxygen atoms floating around at the end. So you can't just make up stuff to add to the equation. So we don't add extra products that aren't there. What about, can we change this from H2O to H2O2? That would work. Is that okay? Does anybody know what H2O2 is? You know what that compound is? Is it water? It's not water. It's called hydrogen peroxide, which is not the same as water. Don't drink it when you're thirsty. It'd be bad for you. So if water is not the same thing as hydrogen peroxide, then we can't simply change the subscripts on our compounds because we're changing what those compounds are. So how do we bring this into balance? How do we make sure that we have the same number of atoms on each side without doing the things that we just said we couldn't do? Anybody see another way to make that work? Yeah, we can react them in a different ratio. So this problem isn't really a problem of like something disappearing. It's really saying this isn't the correct ratio. 1 hydrogen molecule and 1 oxygen molecule do not make 1 water molecule. They react in some different sort of ratio. So for instance, what if instead we reacted 2 hydrogen atoms with a water molecule, or with an oxygen molecule, and then we made 2 water molecules instead of just 1? Now if we count those things up again, we've got 4 of these, 4 and 2, and now it works out. So what that's really telling us is that hydrogen and oxygen have to react in a 2-to-1 ratio, not a 1-to-1 ratio. And the way we express that in the chemical equation is by putting these numbers out in front of the chemical formulas that we call coefficients. So we put a 2 here to represent 2 molecules of hydrogen instead of just 1. And we put a 2 here to represent 2 molecules of water instead of just 1. And now that all works out. So the final step in writing a chemical equation is always something called balancing the equation, which is changing the coefficients, changing the ratios, so that you have the same number of each atom on each side. So that's kind of like the theory behind that. Now let's look at the actual technique and how we do that, like how we go about balancing an equation in a way that's kind of systematic and make sure that we do it right. So here's a chemical equation. of combustion of methane gas. That's natural gas, or most of natural gas. It reacts with oxygen and forms carbon dioxide and water. So whenever we're going to write down a chemical equation, one of the questions we have to ask is it balanced? Does it have the same number of atoms of each type of atom on both sides? So what you want to do to figure that out is count them up. On the left side, we've got 1 carbon, 4 hydrogens, and 2 oxygen. You see where I get those numbers? So we use the subscripts to know how many per compound, and then we add them up. And I'm saying that for the entire side of the equation, for all the reactants together. On the left side, or on the right side, sorry, I've got 1 carbon, 2 hydrogens, and 3 oxygens. 3 oxygens because we got to add the 2 from the CO2 and the 1 from the H2O together. And so looking at those numbers, and if you kind of write them like that, you can see right across that those numbers are not equal. The carbon's balanced, but the hydrogens and oxygens don't. So that tells us we need to balance the equation. So when we did the hydrogen one, I kind of just said, oh, we can add another hydrogen molecule. But there's really a better way to do this when we're looking at the equation. So we start with whatever element you want to start with. We'll talk about why why we would start with some and not others in some situations. Carbon's already balanced, so we're not going to do anything with that. Hydrogen is not. We've got 4 on the left and 2 on the right. So rather than saying that means I need 2 more on the right, because that can get a little confusing, what we should say is, how can I add a coefficient so that there are 4 total on the right? Because we want the 2 numbers to be equal. So what coefficient would you add to make 4 total hydrogens on the right? You put a 2 where? In front of H2O, right. So I'd put a 2 there. And then this is the really important part. You have to correct your numbers below. Because when you put that 2 there, you don't just change the hydrogens, you change the oxygens also. Because that 2 applies to the whole molecule, the whole water molecule. So now we've got 4 hydrogens on that side. And we also have 4 oxygens on that side. Because now we have 2 from the CO2 and 2 from the H2O, the 2 O's. So that's balanced. Then the last thing that needs balancing is the oxygen. We got 2 on the left and 4 on the right. So we need to change the coefficient on the left to get 4. So how are we going to do that? Add the 2 right on the oxygen. And then we recorrect this as 4. And now everything's in balance. The nice thing about these problems is you can always tell if you're right or not. If they're balanced, you're right. If not, you're not. So you can look at the numbers on each side. You can count those atoms up and see if they match or not. And that'll tell you if you've balanced the equation or not. All right. So let's try some of these. And as we try some, we'll get into some different situations that, and I'll give you some more hints for how to figure this kind of stuff out. So one thing we might want to look at is what happens if we have polyatomic ions. I'm going to leave the states off here because we're just worrying about the balancing for now, but we could put them in also. So if we do an inventory on this one, and you can go ahead and work ahead of me if you want. One thing I would do here, so I've got 1 mg on this side, 1 ag, is I would recognize NO3 as the polyatomic ion nitrate. So rather than counting up individual N's and individual O's, I can recognize that NO3 stays NO3 for this whole equation, and therefore I can just count it as NO3 and save myself a little bit of work. So I can say there's 1 NO3 on this side, and this side's got 1 mg one Ag, and two NO3s. Now, if you don't like that, that's fine. You don't have to do it that way. You can just count individual N's and O's. But it can save you a little time if you recognize that that stays the same, and therefore you don't need to count it twice, to count everything twice. So to balance this one, everything looks in balance except the NO3. But the only way I can change the NO3 is by putting a 2 over here. So that ends up affecting not only the NO3, but also the silver, the Ag. And then I have to correct that over here by putting a 2 up there. So just please remember that you can't change the formulas. You can't change the subscripts. You can only change the coefficients to bring these things into balance. Okay, let's try another one. This is combustion of butane. See if you can do this one. I'll give you a hint. You might run into a little bit of trouble. That's okay. We're going to talk about that trouble. See how far you can get. Any problems with it?
It's just going to be this easy. Like, I didn't know what I have here. Come over here and see what I have. So I'm doing now. Balance these out. And that's going to work by going and
What do you got the wrong number there? You got 4 on this. You put a 3 here. 3. Don't think of it as common when we're doing this. What number needs to go there? That's what it means. So the 4 there, that's got 4.
so it already has one.
Right. So if you add a 3 more to 1, 2, 4.
Right.
Yeah, it moves the somebody sees that. 4, right? So that's 3. With the 3 there, that's still including that first.
So I need 4.
Right. Is anybody getting stuck at a particular spot here? Where it's not working out? Yeah. All right, let's go through it.
Yeah.
See how it works. All right, so first thing is to count everything up. So 4C, 10H, 2O, 1C, 2H, 3O. Now, where do you start? Well, you can start at any atom you want, except for one thing. You don't want to start with the oxygen. The reason you don't want to start with the oxygen is because it's in too many different compounds. If there's any atoms that are in multiple different compounds on both sides or on one side, you want to leave those to last because we don't know how to change them. Like the one on the left says 2, the one on the right says 3, but it's actually 2 and 1. So does that mean you should change the H2O first, or should you change the CO2 first? And then this, like, there's too many decisions, so you can't do that. So save those until last. It doesn't matter if we start with the C or the H. That really doesn't matter. So let's start with the C because we wrote that first. We've got 4 on the left, we've got 1 on the right. So we need to bring those into balance so that there's 4 on each side. 2 from the CO2 and 1 from the H2O. So if we put a 4 here, now we recalculate our amounts. That gives us 4 C's. And now instead of 3O, we have 8 from the CO2, 1 from the H2O. That's 9. Because each CO2 has 2 O's, and now we got 4 of them. Right. Times the 2, yep. Yep. And if you don't see that, you can write it out. So if we actually drew out 4 CO2 molecules, OCO, 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 you could count up and see that there's 8 oxygens there and 4 carbons. So that works. We got our carbons in balance. Let's balance the hydrogens. We've got 10 on the left. We want 10 on the right. So to do that, we got to put a 5 here because there's 2 per molecule. So if we have 5 molecules, that's 10 total. So that gives us 10 O's, or 10 H's. And now we've got 8 plus 5, which is 13 O's. So carbons are in balance, hydrogens are in balance. Oxygens are not. So what do we need to put on the left to make it add to 13? 8 plus 5? 4 CO2s. So you got an O, you got 2 O's in each CO2, and there's 4 molecules. So that's 8 total O's. And then add to the 5 from the 5 waters, that's 13. So is there anything we can put in front of O2 to make 13? Not really, right? Yeah. 6, you think you could do like 6.5? Not really, no, it's got to be whole numbers. So that doesn't quite work. Because if you put a 6 in front of the O2, you've got 12. But if you put a 7, you got 13, you got 14. So that doesn't work. So the way you figure that out, this is something that happens a lot. So when this comes up, what that tells you is that you have odd numbers on the right, even numbers on the left. You need to change everything into even numbers. And the way we change odd numbers into even numbers is to double them. So we're going to double all the coefficients in this reaction. So we're going to go 2, 8, and 10. Because we've doubled all of those, we shouldn't have to rebalance any carbons or any hydrogens. We can just, because we got to change that one anyway. So we could have put 2 in there, but we know we have to change it anyway, so we just left it. We can redo our totals now. 8 C's, 20 H's. We still got 2 O's there. Over here now we've got 8 C's and 20 H's. And now instead of 13 oxygen, we've got 26. 16 plus 10. So now we can put a 13 here to bring those into balance and to get 26 oxygens. 13 times 2 is 26. So a couple of things to learn from that. This comes up where you may need to double the whole thing. So if you can't seem to get things in balance, it either means one of your formulas is wrong or you need to change everything, change all the numbers. There's definitely trial and error involved in this. So it seemed very clear when I went through the steps, but it's not always that way. And when you're looking at it yourself, it may not be clear to you what to do. So there's always a place in these types of problems for just trying some different numbers and trying to figure out what might work. That happens.
Can I just ask you a
Yeah.
math portion of this?
Sure.
So when we're putting a different number in front of the H or the C, and there's more than 2 elements there, so that 5 is going to be multiplied by 2. Wait, I just lost my train of thought.
Right, it'll be multiplied by the subscripts, the little numbers,
Right, so it's going to
for
be
each,
10,
for those particular atoms. So it's going to give you 10 H's
and then the 5.
and 5 O's. Or when we put the 10 there, 20 H's and 10 O's. Yeah. Okay. Let's try another one.
You won't include any of these on a test, right?
Well, this will be part of it, but it'll be more fun because I'll just say things like, write an equation for the reaction of butane with oxygen, and you'll be able to write that whole thing. So that'll be fun, right? We'll get there. I mean, not like today, but we'll get there. All right, give this one a try. The decomposition of potassium chlorate gives potassium chloride and oxygen gas. Let's see if you can balance that one. All right, were you able to get this one? Yeah, so how'd you work on this one? What'd you do?
Just put 2 in front
Like that?
and then 2 and then 3.
2, 2, and 3. All right, so does that work? Let's check it out. We got 2 Ks on the left, 2 Ks on the right, 2 Cls on the left, 2 Cls on the right, 6 Os on the left, 6 Os on the right. So it works. So it works. So with this one, if we're thinking through it, the Ks and the Cls are already balanced at the beginning. The Os are not. We've got 3 on the left and 2 on the right. The only way to bring a 3 and a 2 into balance is to kind of switch them, kind of like when we were building those formulas. So we got 2 of the 3s and 3 of the 2s, right? It's called least common multiple because they can both be 6. So that's something that you'll see in these equations sometimes. Let's try another one. So another way that we want to be able to write chemical equations is from words. It's a little bit bigger though so we can see it. So I can write a chemical equation in a sentence like aluminum metal reacts with aqueous copper 2 sulfate to form aluminum sulfate. That should be aqueous. And copper metal. So that's another way to write an equation. Can we turn that into a balanced equation? Give it a try. So hopefully you see on this one that not only do you need to be able to balance the equations, but you need to know how to write the formulas properly, because if you have the wrong subscripts in the formulas, then the equation's not going to work out either. So it kind of really builds on what we've already done. Working on that one for 4 minutes. Almost out of time, but we got a little. Go ahead if you've already written stuff down and show it to people around you. See if you've come up with similar things. If not, talk about why they might be different. No, that means in water. So the solution in water that just says the state. So you put S for this, it's metal, it's a solid metal. That's not quite great formula, but that's it. How do you feel about that? Okay. All right, let's go through it. Let's see if people got it. So the first thing to do is to build the compounds. So keep practicing that because you don't want to spend too much time doing that as we're going to be doing more and more stuff with these equations. The aluminum metal is just going to be Al. And since it says metal, we can know the state that that's a solid. Aqueous copper sulfate, copper 2 sulfate. That's copper 2 plus, and we know sulfate is 2 minus, so that's just going to be CuSO4. And that's aqueous. So we put a little AQ there. And what's that going to form? Aqueous aluminum sulfate. Aluminum sulfate is Al2SO4 3. That's one we might have to spend a couple minutes to build because aluminum is +3, sulfate is -2, so we got to bring those into balance, and we get 2 and 3. That's aqueous as well. And then our final product is copper metal, which is just solid copper. So once we got those all down, assuming those subscripts and formulas and everything are right, then we can start doing the balancing. So I'm going to show you another shortcut to balancing. For those of you who don't want to do a shortcut, keep going with the full, like listing out all the elements to check. But if you can kind of see it, what you can do is balance by what we call bouncing back and forth. We bounce from one side to the other side of the equation. So I might look at this and say, okay, I see 1 sulfate on the left and 3 on the right. So then I'm going to balance that out by putting a 3 here so that I got 3 sulfates on both sides. When I change the sulfate, I also change the copper. So now I'm going to bounce to the other side to fix the copper. Now the copper is fixed. That's in balance. Then that doesn't change anything else, so I just look at the rest of the equation, make sure I didn't forget anything. And I noticed that I forgot the aluminums. They're not in balance. I haven't checked those. I got 2 on the right, 1 on the left. So I should put a 2 here, and then that should all be balanced. Always a good idea at the end when you think everything's balanced to go back through, add up the elements on each side, and just make sure that everything is indeed in balance. All right, questions? Let's
We
do.
can't memorize all those
Yeah.
ammonia, carbonate,
Mhm.
bicarbonate, all those, and people said it was going to be important because we have to go back to it.
Mhm.
So sulfate is SO4 with a -2.
Right.
So where's -2?
Well, that's the charge on the sulfate. So in a compound, compounds are neutral. When you have multiple things coming together, they're neutral. So if sulfate is -2, copper 2 is +2. So you put those two together, you have a neutral compound. +2 -2. That's going to be neutral overall. All right, let's try one more. Same style. Make it a little bit bigger. We're going to do this one in lab next week on Tuesday. Solid, if I can spell, calcium carbonate decomposes to form solid calcium oxide and carbon dioxide. See if you can write out a balanced equation for that one. almost out of time, so I'm gonna show you this one. Calcium carbonate is CaCO3 plus 2 calcium minus 2 carbonate. And we say decomposes. We didn't really talk about the different types of reactions yet. We'll get into that next week. But that really just means that that's the only reactant. That thing breaks down itself to form these other things. And the things that it's going to form are calcium oxide, CaO. Also, that doesn't require any subscripts because it's plus 2 for calcium, minus 2 for oxide. And then the last product is carbon dioxide, which is CO2 as a gas. Now, we didn't know from the question that carbon dioxide is a gas, but we know that usually carbon dioxide is a gas, so we can assume that. Is this one balanced? Yeah, it is. So this one's balanced right there. We don't need to add any coefficients. It's just all ready to go. All right. So lab on Tuesday, we'll be doing a lot of these reactions, lots more practice balancing equations and writing equations. Please work on that stuff this weekend, and please work on going back and looking at some of these compounds, because you got to be able to build the compounds first before you can balance the equations. Yeah. You could balance it as, yeah, because in this case it doesn't stay the same throughout the equation. So when you're balancing, it makes more sense to have the carbon. Right. You can only do that if it stays the same. It doesn't go down. Right. So you got calcium ions, carbonate ions. No, it's not a name. Nope. Tuesday. Oh yeah, the periodic tables. Drop those off, please. Thanks.
Very excited on it. It's not that I wanted this, because I have a great time. You're like everyone, but there's no way I could ever do it.
No, we don't have that.
Like not even if I attempted.
Right. We don't have yeah, we do, but that's how we do a bunch, and you can drop them.
Okay, so like I began on the first year, and then this one was fine. Like let's say, how many more do I like to rely on?
Most semesters it's 8 or 9, so total. So that would be drop it.
Just like this one. You got a, what'd you get?
What?
Yeah, I can hear it.
There's a quiz on Thursday.
There's another quiz on Thursday?
Yeah.
And it's going to be Tuesday?
Probably just today. Probably
Just today?
Okay. Yeah.
See you.
All right.
Have a good,
Yeah.